Hello everyone. So after we have finished the chapter gravitation, now we are going to start a new chapter which is mechanical properties of solids. Okay, so there are different properties that solids exhibit, but of those properties we are going to see one property which is very much relevant to the physics, or per se to the mechanics of materials, and that property is elasticity. So with respect to solids, we are going to explore this property of elasticity. What exactly is elasticity? What is the use of elasticity? When the materials exhibit this property of elasticity, what do they exactly do? All these things, what is the molecular origin of elasticity? We are going to discuss all these things. So elasticity, to understand what is the property elasticity, consider this one example of a spring. Let us say you have two boxes tied to the two ends of a spring, or let us say you are holding this spring with both your hands and you extend the spring. Then what will happen? You apply the forces on both the boxes basically. Then what will happen? The length of the string will increase, or rather the length of the spring will increase. So spring will start looking like this, right? And now what you do is, whatever forces you are applying, you just remove them. You release the boxes. Then what will happen? The spring will jump back to its original position. Now the property by virtue of which the materials, they regain their shape after removal of deformation forces is called as elasticity. Let me repeat the definition. The property of solids by virtue of which they regain their original dimensions on removal of deformation forces. When you remove the deformation forces, they regain their original dimensions, and this property is exhibited by solids. It is called as elasticity. Now what is plasticity in that case? Plasticity is basically exactly opposite of elasticity, wherein the materials do not regain their original dimensions. So consider an example of, to exhibit elasticity, you can consider the example, the best example is of rubber band. You pull it from both the ends and release it, it will regain its original dimensions. Now the same thing happens with so many solids, but the only thing is, for example, if you take a steel rod and you try to extend the steel rod and then release it, it bounces back to its original length. Now why don't you observe this in day-to-day life? Because the forces that you tackle in your day-to-day life, let us say you apply a force on steel rod. Now how much force do you think will be needed to extend the steel rod by 1 millimeter length? The force is huge, so you cannot apply it by your hands, but that force can get applied, or in fact it gets applied when you are dealing with machines, when you are dealing with constructions, when you are dealing with bridges. So many places you have metals, concrete and many other solid things playing their roles, and the forces that play in all these applications, in day-to-day life applications, they are huge in magnitude. So when a huge force is applied, these materials, they deform under these forces. So either they get extended, their length increases, or their length may also decrease under the application of a force. So a typical example of decrease in length is, when when a building is built and the people start staying in the building, then what will happen is, because of the weight of the people and weight of the things that you bring in your home, because of all this weight, the building gets compressed under the load. So who bears this load? It's the concrete of the building, it's the iron rods that are inside the walls in the building. All these things, they hold the weight. So under the action of all this weight, the self weight of the building as well as the weight of the things and the people that are inside the building, the concrete and the rods, they undergo a compression, they undergo a reduction in the length. Now, how much force can they sustain? If you want to know this, consider an example of a bridge. The various elements inside the bridge, they undergo a compression or extension depending on which type of forces are acting on it. So whether they will be able to sustain it or whether the bridge will collapse. There are so many things, the vehicles, the constructions, and so many things are there in day-to-day life that have the study of that, that would need a study of mechanical properties of solids, and especially this particular property, elasticity. So to understand elasticity, these were the examples. Now to understand plasticity, Plasticity is exactly opposite of elasticity. So this won't happen. So if you apply a force on something, it might be an extending force or compressing force. In either case, the material won't be able to get back its original dimension. Now it could be a partial plasticity or total plasticity. So for example, if you let us say you take a plastic object, say a plastic bottle, and you compress it, an empty plastic bottle, and you compress it, then what will happen? The bottle's shape would change, it would get compressed, and when you release the force, when you release the deformation force, the bottle tries to get back to its original dimension. A thin plastic bottle I'm talking about, so it tries to get back to its original dimension, but it isn't able to do that. So some amount of deformation is still left in the bottle. So that's the plasticity behavior. It is not able to revert back to its original dimension. Take some mud, solid mixture of soil and water. So take that mud and put it in one form, and then try to deform it. When you try to deform it, it gets deformed, but then it doesn't swing back to its original form. So that's the plasticity behavior that is exhibited by solids. So solids can either be elastic or they can be plastic. Now why are some solids, or many of the solids, why do they show elastic behavior, and why are there many other solids which show plastic behavior? The reason lies in this molecular origin. So elastic behavior can be explained with the help of studying the molecules and the interaction between the molecules. So if you consider a crystalline solid, let us say, or the simplest example would be to consider a metal. You would see a crystal lattice. So basically the molecules, atoms and molecules inside that metal, they are arranged in a particular fashion, and it's not just a two-dimensional, but it's in fact a three-dimensional fashion. So it could be of cubical structure, or it could be of hexagonal structure, it could be of any other different form, but that form is repeated in the entire volume of the material. The same, let us say it has a cubical shape, then the same cube will be repeated again and again and again in the entire material. So what happens is, now this is one molecule, and this is another molecule, and this is third molecule, and this is fourth molecule, and so on. So this entire crystal lattice, this is called crystal lattice. So this entire crystal lattice, the molecules inside this crystal lattice, they hold their specific positions, and they have intermolecular forces playing in between them. So every molecule is being acted upon by several intermolecular forces from all the other molecules. Now what is the origin of these intermolecular forces? It has electromagnetic origin. So basically the electrons and protons that are in one molecule, they apply a force on electrons and protons in the other molecule, and this force is of attractive nature. So there is an attractive force acting on this molecule from this side, and from this side, and from this side, and let us say from this side if there is another molecule over here. So there are several number of molecular forces, intermolecular forces, that are acting on every molecule depending on the form of a crystal lattice it is having. So it could be cubical, it could be hexagonal, it could be some other form. There are different forms of crystal lattice. Now this intermolecular force is basically playing a role of spring force in case of the example that I had told you earlier. So for example, this is one molecule and this is the another molecule. The force acting between them is attractive intermolecular force. So basically you can imagine as if every molecule is connected to other molecule with the help of a spring. Now try to imagine this situation. These four molecules that I am showing now, the springs do not exist in reality. It's the representation of intermolecular force between the two molecules or between the two atoms. Now imagine several number of such molecules all tied to each other with the help of springs, and then if I apply a force for extending or for compressing the length of that particular solid, or if I try to bend that solid, then in that case what would happen is these springs will either extend, or they will get compressed, or they will get bent. So there could be several combinations that can happen if I apply force on either end of this solid. Then what will happen? The springs will resist the deformation that you are trying to cause, and that is the reason why the solid swings back to its original dimension. So if you try to extend its length, the the springs, the hypothetical springs would also expand. This is a model to represent the intermolecular force. So there isn't an actual spring, but we are considering intermolecular force between the two molecules as if it can be represented by a spring. Now there is a reason why you can represent it with the help of a spring, and the reason lies behind studying the molecular theory and how these intermolecular forces, they what is the equation that governs the intermolecular forces and all. So we won't be going into all those details, but take it from me that these intermolecular forces, they can be represented by a spring force. So when that happens, the distance between the molecules, it may increase or it may decrease, and accordingly the spring would either exert the spring might get extended and it would exert an inward force, or the spring might get compressed and it could exert an outward force on the molecules. Now all these springs do the same thing, and entirely the if you remove the deformation force, if you remove the external force, then the object would swing back to its original dimension. Okay, so intermolecular force is giving this property of elasticity to the materials. Now let us see, I was saying that you can either apply a force which is trying to extend the dimension of the object, or which is trying to compress the reduce the dimension of the object, which is trying to bend the object, and so on and so forth. So there could be different ways in which you can apply the force on the object, right? Like we have seen, you can try to increase the length of the object, and you can try to decrease the length of the object, you can try to bend it. There is something called as shear force, there is something called as the volumetric force, so basically pressure force. So let us say I am having a solid object and I want to decrease its entire volume. I'll have to apply pressure from all outside. Imagine a balloon which is being compressed. So there could be several ways you can apply forces on the solid object, and accordingly the object should respond. So the way you apply force on the object, the way in which you apply the force on the object is categorized under stress, whereas the way in which the object responds is categorized under strain. So let us see the definitions of stress and strain. So stress is defined as to understand stress, you should first understand that this stress has some linkage with the intermolecular force that we were talking about before some time. So I had explained that if you try to take away the two molecules, then the hypothetical spring will try to bring them back, and if you try to compress them against each other, then the hypothetical spring will try to push them away. That means if I consider this rod, let us say, and if I try to apply forces on either of the ends, the molecules would tend to go away from each other, and in that case the springs would try to bring them back. So if I take a cross section, a hypothetical cross section of this rod, I would see that atoms and molecules on this left hand side and atoms and molecules on this right hand side, they are pulling each other. So basically they are trying to resist the deformation. So these molecules will have a rightward force on them, and these right side molecules will have a leftward force on them, and so on. So basically they will try to oppose these external forces, and the internal resistance by the molecules to resist the deformation, the internal resistance exerted by molecules to resist the external deformation is called as stress. Now that internal resistance is always taken per unit area of cross section. So let us say you apply force F on this side and force F on this side, equal force on either side, just to ensure that the rod does not travel left or right, but we are just trying to increase its length. If the forces are unequal, then along with change in the length, the rod will also have a translational motion, which we don't want to have as of now, because we don't want to complicate the situation. So let us say both the forces are equal and the molecules, they are trying to go away. You are pulling the molecules away. So what will happen? Let us say one molecule is over here and the other one is here. In between them is the hypothetical spring. So if you pull this rod away from each other, then there will be a force, an intermolecular force, which will try to restore the position of these molecules to the original force. Now that intermolecular force per unit cross-sectional area over here, intermolecular force per unit cross-sectional area over here, it is called as stress. But do you realize that that intermolecular force will also be equal to the force that you apply? You can just get it by drawing an equilibrium or rather FBD of this body. So you will have F from over here, and in between the molecules there exists a force in this direction for this left hand side part of it, and that's an intermolecular. So this is intermolecular force, right? And on the other part also I can show this intermolecular force. So now for the equilibrium of this part, I can say that external force is equal to intermolecular force. So if I want to find out stress, I can say that stress is equal to intermolecular force per unit area, or I can say it is also equal to force applied per unit area. So stress is defined as force per unit area. Force per unit area. And hence the unit of stress is Newton per meter square. In case of strain, as I said, stress is the way you apply a force and strain is the way the body responds. So strain is defined as change in dimension of the body. Now which dimension? Are we talking about a change in the length, or are we talking about a change in area, or are we talking about a change in the volume, or what are we talking about? That I'll tell you later. So change in the dimension per unit original dimension. That's the formula for strain. So stress is defined as applied force per unit area or internal resistance force per unit area. So it is properly defined as internal resistive force per unit area, but it so happens that internal resistance is also equal to the applied force, and strain is defined as change in dimension per unit original dimension. Now once these two are defined, we will see what kind of what will be the dimension of this change in dimension per unit original dimension. So it will have no unit, right? Because if this is taken in meter, this will also be in meter. If this is in meter square or meter cube, accordingly this will have same dimension. So all in all, strain does not have any unit. Now what kind of stresses can we encounter? So basically, what are the ways in which we can apply forces on the body? As I said, we can apply a tensile force, we can apply a compressive force, we can apply a force which is trying to reduce or increase the volume of the object, or there is another type of a force that I will tell you now. So first way to apply force is to apply force on a body which has linear dimensions. So for example, a rod. We can apply either a tensile or we can apply a compressive force. So that would either increase the length of the rod or that would decrease the length of the rod. So that is one way we can apply force on linear objects. We can try to change their dimension. So this force, whatever force you apply per unit area, is denoted as stress. I mean, it is called as stress and it is denoted by sigma. Okay, so this is first longitudinal force that we are talking about, a force along the length, a longitudinal force. The strain also in the same context will be defined as, now if you apply force F, what would happen to the rod? This rod would undergo a change in the linear dimension, so its length would increase if you are trying to extend it, its length would decrease if you are trying to compress it. Now if you apply forces by hand, you won't be able to see an appreciable change in the length. But if you apply a force by using some machine, or if you take, instead of a steel rod, if you take a rubber rod, let us say, then you would see an appreciable change in the length. So let us say the change in the length that you see is delta L and the original dimension is L. Then the ratio of delta L by L is defined as longitudinal strain denoted by epsilon. So that's the first type of a strain we can have in case of a longitudinal stress. The second type of a stress that we can have is shear stress. So this is longitudinal stress and this is longitudinal strain. The second type is shear stress. Now when can you have this? Let us say you have a box with you and the box you fix it to the floor. So you won't allow the bottom of the box to move, and you apply a force on the top of the box. Can you imagine what would happen? The box would bend in this direction, right? Because the bottom is fixed, you cannot allow the bottom to move, but you are applying a force on the top of it, then the box would bend like this. To imagine what exactly is happening over here, you can consider an example of a thick book. Take a very thick book and apply and fix it at the bottom and apply a force on the top cover of the book. The book would bend like this. So that kind of a force is called as shear stress. I mean, force per unit area is called as shear stress. So which force are we talking about? We are talking about this force per unit area. Which area are we talking about? The area on which the force is being applied. So it is being applied. If you look at this box in its 3 dimensions, then you are applying a force on this top surface. So the area of this top surface has to come in picture. So force per unit area, where area of the top, not the cross sectional area of the top on which the force is being applied. So that is called as shear stress, denoted by tau, denoted by letter tau. The unit is same, Newton per meter square, but area in here is the area at the top surface. That means the area which is parallel to the force being applied. Here the area was perpendicular to the force being applied, right? And that's the difference. So here it was called as longitudinal stress and longitudinal strain because they were happening along the length. In here they are called as shear stress. Shear stress. So every layer basically of this object is moving on the top of the other layer. You can consider as if this object is in the form of layers, like a book which is having several number of pages, and you push the top page of the book. What will happen? All the pages will slide over each other and the entire book will bend. Similar thing happens in case of all the solids. So in that case, the force that is being applied is called as shear stress, denoted by tau. Correspondingly, we will have second type of a strain which is called shear strain. And shear strain is defined as, now in this case, this was the original position of the box, original orientation of the box, and the box bent in this direction at an angle, let us say theta. Then in that case, tan of this theta is denoted as shear strain. So shear strain is given by tan of this angle theta, or in other words I can say how much change in x directional, that means how much change does its top surface take. So basically, by how much distance does its top surface move per unit height of that top surface. So opposite side divided by adjacent side for this particular triangle, if I take, then that is equivalent to tan of theta. Tan of theta is opposite side by adjacent side, where opposite side is the distance through which the top surface moves and adjacent side is the height at which the top surface is. The ratio of these two is defined as shear strain. So again, notice that it does not have any unit. Now the third type of a stress that you can apply. So one way you can apply force on the body is to change its linear dimension, to increase or decrease its linear dimension. Second is to change the angle at which the body is. So basically change its orientation. And the third way you can apply a force on the body is to change its volume itself. So for example, as I was saying, consider an example of a balloon, or in general you can consider an example of a solid object. In that case, let us say you apply force on this solid ball. Then what will happen? Let us say you are taking a ball that is made up of rubber, an entire solid ball. You apply pressure from all sides, all over the surface of the ball. What would happen? Its dimension would reduce. So let us say its original volume is V, and now the volume has reduced. So let us say volume reduces by delta V, the reduction in the volume. So original volume minus final volume. The difference in the two is delta V, let us say. And in that case, the pressure that you are applying from outside. Now, how do you define pressure? Pressure is defined as force per unit area. So, which area are you applying the pressure? Which area are you applying the force? You are applying the force on the entire surface of the ball. So, the force that you are applying per unit surface area of the ball is defined as pressure. So, this third type of a stress is pressure itself. It is called volumetric stress. Volumetric stress, which is pressure itself, force per unit area, where this area is surface area that we are talking about, and how much force is acting on that surface, that is pressure itself. That's the third type of a stress that you can apply on the object, and because of that stress, what would happen? The object would undergo a change in the volume per unit original volume. That's the volumetric strain that you are talking about. So volumetric stress and volumetric strain that we are talking about. So these are three ways in which you can apply stresses on the objects to change their original dimension, to change their dimension with respect to the original dimension. So in the next lecture, we'll be seeing what is the relationship between the stress that you apply and with the strain that happens with the object. So basically, if you apply a particular amount of stress on the object, then how much will the object deform? There is a particular relationship between these two, which is as expected, right? You cannot say that if you double the amount of stress, then the strain in the object remains the same. The strain would also increase. If you make the stress half, then the strain should also become half. So that means there should be some relationship between stress and the strain. So in the next lecture, we'll define this relationship, we'll define what is Hooke's law, and so many other interesting things we'll do in the next lecture.